Okay, let's work through this. We're dealing with 2.3 linear equations, and to solve linear equations, let's use the integrating factor method. Okay, again, solving first order differential equations. We've looked so far at separation of variables and now integrating factor. Separation of variables we could use to solve either linear or nonlinear equations as long as they're separable. Linear, let's see, integrating factor can only be used on linear equations. So if your first order equation is linear and it's separable, then you have a choice of integrating factor or separation. If your differential equation is nonlinear, integrating factor cannot be used. We would have to use separation. So integrating factor can only be used on linear equations, and those equations need to look like this, where you have a coefficient on the y prime, coefficient on the y, and those coefficients need to be constants or depend at most on t, and then the right side, same thing, constant or depend at most on t, and if the right side is equal to 0, then we call the whole equation homogeneous or homogeneous. If the right side is not 0, non-homogeneous. Then if we're going to use integrating factor, we need the leading coefficient to be a 1, so we're going to divide it into the whole equation. So here we take that equation, a1 of t, divide it there. Then we get a 1 y prime. We get this new coefficient there. Let's call them p of t and f of t. And when you have equation 3 like this, that's called, it's a standard form of an equation, and you need the equation standard form to begin the integrating factor solution. That's what we're looking for, and we're going to define it on the largest non-unioned interval. We'll call it I, where both the p of t and f of t are continuous. Then we're going to need to find the integrating factor. Not only is it a process, but it's actually a thing, and it's mu of t is e to the integral of p of t dt, where p of t is that coefficient there. We're going to, once we find it, we'll multiply it on both sides of the differential equation. The left-hand side will always become the derivative of, or present itself as the derivative of, integrating factor and dependent variable. So let's show you how this works. We have 1y prime plus 2y 3 e to the t. The standard form is 2 and 3 e to the t continuous, and it's continuous for all values t. So there's our interval. Then find the integrating factor, mu of t, e to the integral p of t. P of t was a 2. So e to the integral of 2t dt, we get e to the 2t then plus a d, and in a little bit you'll see why we don't need that constant. Multiply both sides by mu of t. Here's our equation, the left side there, right side here. And remember how exponents work. You got e to the 2t plus d. That's e to the 2t times e to the d on the left side and the right side. The right, they'll cancel there and there. So we don't need that constant d, because it's just going to cancel later anyways as e to the d and e to the d. So let's take that e to the 2t, let's distribute it there and there. And that's showing up here. The right side, let's multiply those. So that's a t plus 2t. And now, okay, right side becomes 3e to the 3t. Then the left side, look, we have this here, the whole left side, when we multiplied the integrating factor times the left-hand side. It will always become the derivative of the integrating factor in the dependent variable. And that's what this is. If you were going to differentiate, first function and second function, then this is the first function derivative of second plus second function, and then the derivative of the first, 2e to the 2t. That's why we're writing it as the derivative of those things. Then the next step is to integrate. But when you integrate the derivative of that, then the integral here and the dt, they wipe away the derivative. It just leaves you with the integrating factor and the dependent variable. Right, I actually have to integrate. Here's our antiderivative. Then we're going to solve for y. So divide by e to the 2t on the left side and the right side. We're doing that here and here with e to the 2t. Left side, they cancel. Right side, e to the 2t goes into e to the 3t and the c. Here they reduce to e to the t. Left side or right, it's c over e to the 2t. So c e to the negative 2t. And then just to mention that this is a transient term because it goes to 0 as t goes to infinity. So all of this is our one parameter c explicit solution. Again, explicit because it's y equals and then just stuff with t. All right, so let's solve one together and go from there. First thing we need to do here is put this in standard form. So this term needs to go to the left side. We would need dy dt minus 1 over t plus 1. Y is 4t squared plus 4t. Then find your interval. We're looking at this. So that's our f of t. It's continuous on all values t, negative infinity to infinity. Then this one, p of t though, continuous on negative infinity to negative 1. So our interval I, we need to pick either this or this one for a non-union interval. And notice y of 1 is 10. That has an input t being 1. That t equals 1 needs to exist either here or here, and it's in this one. So we're going to pick this as I, since t equals 1, our initial condition is in negative 1 to infinity. Okay, let's keep going. Now we need integrating factor. Mu of t is e to the integral negative 1 over t plus 1 dt. Okay, this is more tricky. E to the negative natural log absolute value t plus 1. Move the negative to the exponent. Cancel e to the natural log. So we get 1 over absolute value, 1 over t plus 1. And then this will either equal a 1 over t plus 1 or a negative 1 over t plus 1, depending on whether or not t plus 1, 1 over t plus 1, is it positive or is it negative? If 1 over t plus 1 is positive, then we go with its positive self. If this is negative, then we need to do negative of the 1 over t plus 1. Because if this is negative as it is, then adding the extra negative sign on the out front will make all of this positive, which is what the bars do to something that's negative. Now, on our interval, -1 over t plus, or -1 to infinity, this is positive on positive on. So we're going to go with this as our integrating factor. All right, so now we need to make our equation. We're going to multiply the integrating factor on both sides. Let's take those away. Okay. Right side, left side, integrating factor 1 over t plus 1. On the right side, let's multiply those in. That's a 4t squared plus 4t over t plus 1. On the left side, again, we're going to take this, distribute it here and here, but you don't need to show that because we know the left side will turn into the derivative of the integrating factor and the dependent variable all the time. Then we're going to integrate by t. The left side, it's going to wipe away the derivative and just leave you here with dependent variable integrating factor. So 1 over t plus 1 times y, right side. We're going to factor out some things. For t, that would leave us with t plus 1 over t plus 1. These cancel the t plus 1s. So 1 over t plus 1y is equal to, we're just doing the integral of the 4t. So that's going to be 2t squared plus a constant. Maybe let's solve for y now. Y would be 2t squared plus c times the t plus 1. Now we need to recover the constant with initial condition 110. So y is 10. We get 2 plus c, 1 plus 1. This is 2 over here. So that gives us 5 is equal to 2 plus c when we divide by 2. C has to be a 3. So our explicit particular solution is, we're going to use this, but now c is a 3. So y of t is 2t squared plus 3. That'll work. There's our solution. All right, any questions, please reach out. Y'all take care.